In the earlier module, we looked into the operator which is called as the boundary operator. We said the boundary operator operates on a chain and takes it from k plus 1 to k. In other words, what we have is the boundary operator operating on a chain, k chain, will take it to k minus 1. So we can say the mapping is from k to k minus 1, or we can even say, if you want to keep k plus 1 and k as a basic thing, we can say when you are operating it on k plus 1, it should give an output which is in k. So we are using subscripts to represent k chains. So this is something you should remember. So these are chains, k chains. So we will use the word cochain and we will use the superscripts. So when we put k superscripts, what we are talking about are k cochains. So don't make a mistake with the subscripts and superscripts. Make sure that you are following the thing. For subscripts they are called as chains, and superscripts they are called as cochains. So I said the boundary operator is going to take a k plus 1 chain to a k chain. The co-boundary operator does the exact opposite, whereas instead of on the k chain it acts on a k cochain. So let us see what it does. We say the co-boundary operator, represented by the symbol tilde, the small delta, it takes the value that is in C of k, and I said it operates on a k cochain, and the cochain value is written on the superscript, and it gives the value that is in k plus 1. Remember, these are k cochain and k plus 1 cochain. So it takes a value from Ck to Ck plus 1, and that is what we have here in this slide. So what we have is the co-boundary operator takes a value of a k cochain and takes it to k plus 1. So when we have a matrix represented by a set of real number, so what we have is a set of real number. So let us say A1 is given by a set of real numbers. A1 is the boundary operator operating on edges. The co-boundary operator of this, when A1 is real, so the matrix contains only real number, the co-boundary operator and boundary operator are somehow related. So what we have is the co-boundary operator written as delta, small delta, is equal to A k t. Remember, these were the transpose of the boundary operators, adjoint is equal to A k t transpose, which is nothing but A of k. So what we are saying that is, when partial, the boundary operator is a real incidence matrix, the co-boundary operator, which is small delta, is an adjoint of delta, the partial derivative. So this is most important. When this is real incidence matrix, this will be an adjoint of this. So that is what we are seeing here. So if it is an adjoint, this relationship is valid. So that being said, what we have is a very unique property of the co-boundary operator. Remember, I promised while we started this discussion that we are going to avoid using vector calculus and partial differential equation. So until now we have not done that. We have been coming back and forth into some case of vector calculus or partial differential equations, but now I am going to keep up my promise. So I am going to define, using the co-boundary operator, the operators that we use in vector calculus, namely the divergence, the curl and gradient. So let us see what is a physical connection or how the co-boundary operator is related to these operators, namely divergence, curl and gradients, using the simple example. So before I tell how they are related, let me already say what are the relationships. So the relationships are: the first co-boundary operator is nothing but the gradient, the second co-boundary operator is the curl, and the third co-boundary operator is the divergence. I am going to explain you how this relationship is using a simple example as follows. So let us take this case, the case where we have a line with 2 points. So I do the co-boundary operator, the first co-boundary operator on this line on which certain cochains are there. So the cochain on which I am going to operate is defined on the points. So the cochain is nothing but the potential, electric scalar potential, which are defined on those points. Remember, the co-boundary operator transforms a k cochain to k plus 1 cochain. So let us see how this cochain, the 0 cochain, is going to be transformed to 1 cochain. Remember, this is electric scalar potential. Scalar potentials are defined on points, hence they are called as 0 cochains, and we will see how the 0 cochain gets transformed one order higher. So what we are seeing is, when we see here, the value of the 1 cochain is given by this expression. So it is operating on the individual points where the potentials are located. We have phi of P1 minus phi of P naught. So what we have is nothing but the potential difference defined on this line. The potential difference is nothing but the electromotance, which is a 1 cochain. So let us see. So when we do this one, these are defined on the 2 points, which are basically P naught and P1. What we are getting is, we are getting V defined on the line joining this is a 0 cochain and this is a 1. So as we expected, the co-boundary operator is taking a 0 cochain to 1 cochain. Let us see what it does to 2 cochain, and in this case the second cochain is operating on the surface values. So the values what it operates on are basically the boundaries of the surface. So in the boundaries of the surface what we have got are nothing but the potential differences or the electromotants. So the potential differences here is between this point and this point, this point and this point, this point and this point. So what we are computing here is the cochain operating on the potential differences. The potential differences are one cochain, and what we are getting is the definition of the one cochain getting transformed to an order higher. So what we have got here is the values represented as plus V of S11 plus V of S12 plus V of S13. So it is plus because the direction in which we are computing it, they are all in the same direction. If one of them is in the opposite direction, we will have a minus. Similarly, the third co-boundary operator is operating on the volume, and it takes the value that is defined on the surfaces one order higher. So what we have got is the normal component of the D vector, the electric displacement vector defined on the normal components, and we are doing the addition. Whether it is plus or minus depends on the direction in which the arrow is pointing. If the arrow is pointing inward, it will be described as minus. If the arrow is pointing outward, we have a plus. So accordingly, what we see here is the co-boundary operator is able to give us a logical way in which we can define divergence, curl and gradient using one single operator, and this operator is purely determined using the geometrical, or in fact the topological aspect of your mesh or your domain. So this is a big relief, because we do not need to worry about how to compute the gradient, how to compute the curl, how to compute the divergence, because once we have set the way to compute co-boundary operator, regardless of what the object it is operating on, we will be able to find a way to compute the corresponding quantities. In fact, the best way to go ahead is, once we know what is going to be the geometry, we start to define the boundary operator, and remember, in our case they are going to be real matrices. Once the boundary operator is known, the co-boundary operator is normally known. So I am going to write down what I mean by that in a logical way. So what we see here is, once we have the geometry, so what I mean by geometry is the topological aspects. So I know the points, I know the lines, I know the surfaces, and I know the volumes. So what I am talking about is 0 simplex, 1 simplex, 2 simplex and 3 simplex. So once I know all of them, the only thing I need to worry about is how am I going to define the direction for those simplexes. Once I have defined that, I can uniquely define the boundary operators. The boundary operators are here A1, A2, A3 for example. So once this is known, my co-boundary operator is also defined, because it is going to be the adjoint of the boundary operator. And once I know the co-boundary operator, I have already found a topological way to represent the divergence, curl and gradient. That is it. So the entire machinery of differential equation is represented by one particular operator, and then you have everything. So having discussed that, Now we are going to look into some of the properties of this boundary operator more in detail. So I said the boundary operator is going to operate on object and gives the boundary of that. So let us say M, boundary of M. So what we are seeing here is it takes an object M and gives the boundary of M. So if I put here S1, it is going to give me 2 points Pi and Pj, which are the boundaries of S1. Similarly, if I put S2, it is going to give me the values of S1 of I, S1 of j, S1 of k. So ijk are the 1 simplexes that are surrounding the case of a 2 simplex. So assuming that it is a triangle, the 3 sides are given by here, and the signs of it is going to be, whether it is plus or minus, is going to be defined by the orientation that we said. So what is happening now is we are able to find out that the boundary operator is operating on certain simplexes or objects and it gives. What happens when we do the boundary operator on a point? So when you have a boundary operator operating on a 0 simplex, doesn't exist. In other words, when the boundary operator is operating on S0, we get a value 0. So that is one thing that we should understand. Second thing is, when we do the boundary operator twice, the value regardless of what you put, x will always be equal to 0. Let me explain this. So the boundary operator of S1 will be 2 points which are plus or minus P naught, plus or minus P1. When I do it again, what I am doing is I am doing the boundary operator on those points. Because the boundary operator on the points are 0, this will be again 0. Second thing is, if you take, let us say, a tetrahedron and you are doing the boundary operator on the tetrahedron, what you will get is a closed volume. Let us say this is the surface. So I am doing the boundary on this one and I am just getting the surface of this. So this is the surface enclosing this tetrahedron. What happens now is, when I do again the boundary operator on this one, I will get a 0. This will be much more clear when we take a simple example of a triangle. Let us say we have a surface represented by, so this is tetra, so this is triangle. So when you are doing the boundary operator on the triangle, what we are getting is, we are getting a closed contour, that is the contour of the surface. So when I do the boundary operator again on this particular thing, what I see is the boundary of that does not exist, because it starts from a point, it goes in one direction, it goes to other direction, and it comes to the same point. So the point is circular. So when it is circle, the boundary is again equal to 0. So in other words, when we take a circle, remember, topologist is a person who cannot differentiate between a coffee mug and a donut. For him, any closed loop is a circle, same like a circle. And for a circle, the starting point and the ending point are on the same point. And in other words, the boundary of a circle is 0. So that is the logic. The first property what we have got is, we have got anytime you do twice the boundary operator, regardless of what is there x, this will be always equal to 0. So this is number 1. So the second one is, when you are computing the value of a cochain on a chain, it has to be explained bit in a detail. So let me explain this more in a detail. So what I am doing here is, I am computing the value of a cochain on a chain. Remember, the cochain are nothing but physical variables that are located on a particular chain. So if I want to compute the cochain, which is written as a superscript on a chain, what is happening here is, I am basically using the value of the chain, which is written as sigma I equal to 1 to n of k, where the dimension k is the dimension of the simplexes that are involved in the chain. So we have ai s I of k. So this one we know, the k chain can be represented as a coefficient, incident coefficient, multiplied by the value of the k simplex. So what we are doing now is, we are moving the summation out of the bracket. So this is equal to C of k times S I of k. Remember, I told you the value of cochain that are defined on the individual chain, they are represented as G. You remember that we use the word G to represent the value. So let us go back in the slides to see what I mean by that. When we started discussing the value of the cochain, we said these are the values of the cochain that are defined on the individual points. So when we are talking about 0 cochain, we are talking about points of those nodes and their values. So G1 is the values that are stored in the nodes. If Ck is C1, if k equal to 1, we are talking about values that are stored in those edges. Likewise, so these are the values, the Gi's are nothing but the values that are stored in simplexes. So we are going to substitute for that thing here. So the C of thing is equal to G of I. And once you do that, what we will see here is, we see that the value of thing will be written as sigma I equal to 1 to nk A of I G of I, and that is what we have in this slide. This expression can be written as A of I G of I. So now we know that the value of the cochain can be directly obtained from the value of the boundary operator. So in other words, the value of Ck defined on k can be written as A kt conjugate the adjoint thing of that So what we are doing now here is, instead of Ck, we are writing a term like this. You might wonder how this is true. We said the co-boundary operator is the adjoint of the boundary operator, and this is what we got initially. This is the co-boundary operator, and the co-boundary operator is operating on a k minus 1 cochain. It takes the k minus cochain to a k cochain. So that is what we said, the co-boundary operator takes a value that is k to ck plus 1. We said it adds one value. So in this case k is k minus 1, so it has to improve the value by 1. So it takes k to k plus 1, so it has to take k minus 1 to k. So that is what we see here. And the second thing is, we know that we can change the order of this thing such that, so this is again equal to, we can take this, the co-boundary operator, to the other side. So what will happen is, we have c of k minus 1 comma, so the conjugate complex gets away, and what we will get is only the value that is written like this. So this is important. Let me write down this one more time. We said c of k, the cochain operating on a chain, is equal to and we said this is equal to, we take this one here, and when we change the order on which the boundary operator, it goes into the chain, the adjoint goes away. So what we will get is so this is a very important thing, but let me write it down in a more familiar form that you are used to. The most familiar form you are used to is, so I have a cochain, so remember this one is the small delta, it is the co-boundary operator. So the co-boundary operator operating on a c k minus 1, and it is integrated over the c of k is equal to the value what we are getting here. So always the second value or the boundary terms, I told you this one is the boundary operator, which is written as partial derivative operating on c of k, and this one is k minus 1. So this is nothing but the generalized stroke theorem, and this is the most important relationship. So what is happening here is, the co-boundary operator are operating on a particular k cochain, and when we move the co-boundary operator to the domain itself, it becomes the boundary operator, and it operates on c k minus 1. So in other words, the co-boundary operators operating on a k cochain are nothing but the integrands. So these are the integrands, and the boundary operator and the chain are the domain itself. So this is the most important generalized Stokes theorem. So this relationship is very fundamental and crucial for you to understand the relationship between the co-boundary operator and the boundary operator and the k cochain and cochains. So a K cochain is defined on the chain, and when we are defining that way, what we are talking about is the co-boundary operator operating on a K cochain, K minus 1 cochain, and defined on the boundary. So we can basically move the operators in such a way that we can get it. So this is the most important aspect of the algebraic topology. So we get finalized form, which is the generalized stroke theorem. So using that, we can compute the co-boundary operator operating on the 0 cochain as discussed here, and that is what you are getting here. Remember, this is the same value that we defined earlier, and similarly this is the way we define the co-boundary operator operating on a 1 cochain. And the last relationship that we are interested is the relationship between the operators themselves. So as you know from the vector calculus, curl of the gradient is equal to 0, and we know the divergence of the curl is also equal to 0. So this you can verify. We know the co-boundary operator for curl, we know the co-boundary operator for the gradient, the dot product of them should be equal to 0. Similarly, we can also find the divergence of the curl, which is A3.A2 should also be equal to 0. With this, we come to the stop where we have discussed various aspects of the algebraic topology. We have discussed what is the physical meaning behind two classes of variables, namely the source variable and configuration variable. We set the initial theory of algebraic topology from a very simple network, what we considered, where we discussed about K simplexes, we discussed about K chains, we discussed about what is a boundary operator, we discussed about what is a K cochain, and we discussed about what is a co-boundary operator. Having discussed all these things, we also found out the co-boundary operator is in fact the most important operator, which gives us various ways of representing divergence, curl, and gradient. Once we have that, we can also see that they follow certain fundamental geometrical properties given by the vector calculus, namely the curl dot gradient and also the divergence dot curl should be equal to 0. So that way we see that they are related to vector calculus themselves, and in other words they can also help us to get physical connection between algebraic topology and vector calculus. So with this, we will come to the conclusion of this module. In the next module, we will look at how to model Maxwell equation using algebraic topology. Thank you.